Welcome back to Math 104. We now turn our attention towards statistics with a new kind of example. Section 1 of a pre-calculus course had the following final exam scores. They range from 57 to 97, but this is a whole collection of 100 numbers, and it's a little bit overwhelming to look at. Section 2 also had 100 students, and these are their final exam scores. If your eyes are glazing over looking at all these numbers, that's a good reaction. It's supposed to be a little bit overwhelming, and in fact we now live in the era of big data where truly vast data sets are processed all the time and decisions made on the basis of them. So being able to take a collection of data, possibly a large collection of data, and extract some information from it is important. Just at a glance, which class seems to have done better on the exam overall? Well, at a glance, it seems that the scores overall are higher in Section 1 than they are in Section 2. What's maybe not as obvious, just from staring at it, is that in addition to being lower, the scores are also more spread out in Section 2 than they are in Section 1. In Section 1, almost everyone had a score that fell within a roughly 20-point range from the mid-60s to the mid-80s. But a 20-point range in Section 2, say from 40 to 60, or from 35 to 55, does not cover quite as much of the class as a 20-point range did in Section 1. We're going to want to make this idea more precise of what it means to talk about how spread out a set of data is. Now here's a fundamental question. Pat is in Section 1 and received an 84 on the exam. Sam is in Section 2 and received a 70 on the exam. Which student did better? That is actually not as obvious as it sounds. Had they been in the same section, this would have been a much easier question to answer. Pat would certainly have done better. But they were in different sections. Are we sure that they took the same exam? Even if they took the same exam, perhaps the instructor in Section 2 graded much more harshly. So the answer to this question, this comparison of two performances in two different classes, is really not so obvious. We're going to want to have some mathematical tools for thinking about this. Rather than working with the entire dataset of 100 scores from Section 1 and the entire dataset of 100 scores from Section 2, it is much easier to get a sense of what's going on in each section by working with just a sample. There's always a danger that a sample won't be very representative of the whole class. That is a whole issue that we think about in statistics. For now, we're going to take this sample and just try to understand it. Since this is only a sample from Section 1, the mean score, that is the average score, is called the sample mean. Traditionally, it's denoted by X bar. I realize you're thinking that's the complement sign, but in this context, it's a traditional notation for mean. We compute this mean, this average, in exactly the way that you'd think we would. We sum the 5 numbers and divide by 5 because there are 5 of them. This turns out to be 75.2. As we've seen from computing expected values, those are also a certain kind of a mean, a certain kind of an average. It is not surprising when the mean of a certain set of numbers turns out not to be one of the numbers. It is not surprising when the mean of a set of integers turns out not to be an integer. So we've computed the mean of this sample. What does that tell you about the original class? Perhaps the whole class, perhaps all of Section 1, has an average score of exactly 75.2, and perhaps it doesn't. But this is not a bad place to start as an estimate of what the class average is. That is the main reason for working with samples. If it's too difficult to acquire all the data or to process all the data for an entire population, we work with a sample instead, and we hope that the sample we're working with is reasonably representative of the entire class. How about Section 2? Here I've taken a random sample of 5 scores from the 100 in Section 2. Their sample mean, computed in the same way, equals 48.8. So 48.8 is an estimate for the average exam score in Section 2. Now here's an important question when comparing two sets of data. We alluded to this earlier. Which set of data is more spread out from its mean, and which is more clustered around its mean? When we looked at all the scores from Section 1 and just eyeballed them, that they were actually bunched together a little bit more than the scores in Section 2. So given a set of numerical data, we need a way to measure its dispersion from the mean. So it's specifically going to be in relation to the mean that we're going to measure how spread out the data set is. This dispersion from the mean can be computed in a precise way as follows. This is a little bit involved and we'll go step by step. The first thing you might think of is that we should take each score in our sample and see how far it differs from the mean. So 65 differs from the mean by negative 10.2 points. That is to say, it is 10.2 points below the mean. Similarly, 70, a score of 70, is negative 5.2 points away from the mean. That is to say, 5.2 points below the mean. Then a score of 78 is 2.8 points above the mean. 79 is 3.8 points above the mean. And finally, 84 minus 75.2, that is 8.8 points above the mean. Now here's our first temptation. Our first temptation is to say, each one of these differences from the mean is contributing something towards how spread out the scores are within this sample. The fact that 65 is so far away from the mean, that's contributing something. The fact that 78 is different from the mean, well, that's contributing a little bit. There's a temptation to just add these numbers up because each one is contributing something to the dispersion from the mean. And so if we add them, maybe that'll tell us the total dispersion from the mean. And now here's the catch. When you sum these deviations from the mean, the sum equals 0. And that will happen every single time. That's actually not surprising when you think about what an average is. 75.2 is the one number located somewhere roughly in the middle, in some sense, of the data set, so that the total distance of points from the mean from below will exactly balance out the total distance of points from the mean from above. That's just what an average is, a kind of balancing point between those values below it and the ones above it. Adding these up won't help. You might be tempted to just take absolute values, just cross out the negative signs and add them up. There is such an approach, but mathematically it does not work out nearly as nicely. For a number of mathematical reasons, we're going to actually take these numbers and square them. So we're going to take this 65 minus 75.2, that is this negative 10.2, and square it. We will get 104.4. We're going to think of this number as contributing something towards our measure of the dispersion from the mean. This deviation from the mean, this negative 5.2, will also be squared. It will give us 27.04. That 27.04 is also contributing something to our total measure of how dispersed this data set is from the mean. We'll take each one of these deviations from the mean and square it, and when we're done doing that, we will add them all up. Before going on to the next video, complete these computations and find the sum. This will be the sum of the squared deviations from the mean.